Assalamualaikum and hi. So this is video chapter 5, refrigeration cycle part 1. In this video, I'm going to explain subtopic number 1, introduction refrigeration, and subtopic number 2, the reverse Carnot cycle. Thermodynamic application. So in thermodynamic application, we have the thermodynamic cycle, and there we have power generation and also refrigeration. As we all know, power generation is where we generate the power and work to do something, whereas refrigeration, we call some space into a specified condition. So in the power generation, we have a power plant and engine, which we already looked into the previous chapter, whereas engine is the chapter 2 for internal combustion engine, auto and diesel cycle, whereas power plant, we have a gas power cycle and also vapor power cycle. Now we look into the refrigeration, which is first chapter, or chapter 5, refrigerator. Introduction, refrigeration. Introduction, refrigeration. So this is a simplified diagram of refrigerant. As you can see here, the heat is absorbed by the refrigerant, and then here the heat is released to the surrounding. So it is a major application of thermodynamics, as already explained, that the heat in the cold area being absorbed by the refrigerant, and then the refrigerant release it to the hot area or the surroundings. And the device of it is called refrigerator, and we have the refrigeration cycles, and in the refrigeration cycle we have two types of cycle, which is a vapor compression cycle that involve phase change of the refrigerant, and another one is the gas refrigeration cycle, where the refrigerant remain in the gaseous phase. Refrigerator and heat pump. So as we all know, in the normal cases, the heat is transferred from high temperature medium to the low temperature medium. However, for this case, which is for the refrigerator and heat pump, the heat from the low temperature space is absorbed by refrigerant and being transferred to the high temperature space. So we have a same device that using the same principle, which is the refrigerator and also the heat pump. And the refrigerator function is to maintain the refrigerated space at low temperature by removing heat from the refrigerated space and transfer to the surrounding. As you can see here, the refrigerated space is down here, and this is the desired output, QL, with the work net in, and then the heat is transferred to the environment. Whereas the function of the heat pump is to maintain a heated space at a higher temperature by absorbing heat from low temperature source and transfer to the high temperature medium. And this is the simplified diagram of the heat pump. As you can see here, this is the desired output, and this is the space that you want to control the temperature, with also with the work net in. And as you can see from this, we can calculate the coefficient of power per refrigerant, which is equal to desired output divided by required input. It is also equal to cooling effect divided by work input, and it is equal to QL divided by work net in. Whereas for coefficient of power per heat pump, it is equal to desired output divided by required input, which is the same as the coefficient of power per refrigerant. However, it is also equal to heating effect divided by work input. And from this, you can see the coefficient of power for refrigerant is cooling effect divided by work input, whereas for coefficient of power for heat pump, it is equal to heating effect divided by work input. And as you can see, it is also equal to QH divided by work net in. So as you can see here, the difference between heat pump and refrigerant is this value, which is the heating effect and also cooling effect. For coefficient of power per refrigerant is equal to QL, which is the cooling effect, divided by work net in, and coefficient of power for heat pump, it is equal to QH, which is the desired output or heating effect, divided by work net in. And coefficient of power of heat pump and refrigerant can be related by this equation. So coefficient of power of heat pump is equal to coefficient of power refrigerant plus 1. The reverse Carnot cycle. Reverse Carnot cycle. So as you can see, this is the simplified diagram of the reverse Carnot cycle, and this is the TS diagram of the reverse Carnot cycle. And from this TS diagram, you can see that the arrow direction is in the opposite direction of the Carnot cycle. Since the Carnot cycle is irreversible, this process is possible. And in the Carnot refrigeration, we have in the Carnot cycle, reverse Carnot cycle, we have a Carnot refrigerator and also Carnot heat pump. And we can calculate the coefficient of power for refrigeration of the Carnot cycle, which is equal to 1 divided by, in the bracket, TH divided by TL minus 1. And for the heat pump, it is equal to 1 divided by 1 minus, in the bracket, TL divided by TH. However, the reverse Carnot cycle is not practical for refrigeration cycle. And as you can see in the TS diagram, we have this 4 process. And for the process of 2 to 3 here, it is possible if we set the temperature of the device at the constant temperature, since it's in the saturated dome here. And this process is possible. And another process is process 4 to 1. This process also possible. We just need to set the temperature at certain temperature. However, for the cases of process 1 to 2, where the compression of the liquid vapor mixture, it is the liquid at the state 1 is in 2 phases, so the compressor need to handle 2 phases, which is gas and also liquid. So there is no such compressor that can handle, or it is difficult to design a compressor that can handle 2 phases. And another process is process 3 to 4, which is the expansion process of a high moisture content, which I already explained in the previous slide. It is not practical for a turbine. So the solution of this, we need to use the ideal vapor compression refrigeration cycle, which I'm going to explain in the next video. This is the end of part 1 for chapter 5. Thank you, and hopefully you enjoy my video.